let's go.
Okay, we can start. Hello, my name is Mladen. I'm a data scientist, transferred data scientist. I worked as a software web developer for, let's say, about 10 years. Then switched to data science waters. I was working in St. Bridges as a bioinformatics analyst, then switched to pure data science waters, let's say. Driven by the whole, let's say, conference, I want to just emphasize in our field, let's say data science field, the importance of Python, which is maybe even, the difference is even, let's say, more important than in, let's say, other fields of software development, because here the Python has a clear advantage in the last couple of years. So if you just started doing data science 3 years ago, it would be debatable whether you should use R or Python, and let's say those are like two languages that are primarily used in data science. And now if you're just starting the data science waters, there's no, it's a no-brainer. You should continue using Python, or if you know R already, it's a good way to continue using R. This is a poll from KD Nugget's website. It's more of a user-based and user-entered response. So because the question is a bit broad, like the data science machine learning software that you use. So obviously, if you're using scikit-learn, you're also using Python, and et cetera, but the clear rise of usage of Python is more than evident. Okay, let's start with today's topic, recommender systems. So this is some, I don't know, formal definition. Recommender systems are considered as an inevitable part of any larger system that is offering some kind of product service to the final user. I pretty much like the recommender system because they are beneficial to both service providers and the users, and they offer us personalized experience. So they are pretty much everywhere in every website, web portal that you're using. Recommender systems are taking place, and the recommender system algorithms are running in the background to provide you personalized content. These are just some of the random facts, like 35 of what is purchased on Amazon comes from recommender systems, and 75% of the movies that are watched, series that are watched on Netflix comes from product recommendations. Okay, before we continue about recommender systems, just a few words about various rating systems. So we have continuous ratings, like you have a slider, you choose something on a continuous scale. We have discrete systems, stars grading systems that we used to, like rating movies on IMDb or some other website. Ordinal, like the new Facebook strategy, well, new used for, I don't know, several years back, like love, sad, angry, etc. Because they are not, they don't have any, let's say, order in them. Binary, like, dislike, used for news articles and comments, and unary, like on Facebook. Yeah. And also we have to consider that there are explicit and implicit feedbacks. Explicit feedbacks are considered as ratings, and that's, let's say, what are recommender systems primarily based on. But there are also implicit feedbacks used in the system, and that's all kind of, let's say, user tracking that you can or can't imagine that is in present day situation. So viewed items, mouse hovers, and etc. etc. This is well, one nice thing to have in mind. We'll go back to it a bit later, but it's not to mention it's a Pareto principle. Maybe someone already heard of it or not. It's 80-20% rule, and basically that means that 80% of the ratings come from 20% of the users, or come from 20% of items also as well. So we come to the question of types of recommender systems. So there are two, let's say, big areas of recommender systems that are content-based and collaborative, which can be further separated in the user item similarity space and neighborhood latent vector. But not to go with the, fancy words immediately. We will go to each of them and you will see that they are just Okay, and then we have also hybrid models as well, which are some combination of content-based and collaborative-based. Let's say content-based recommender systems are something that was primarily used in the earlier versions of recommender systems. And as the, let's say, the data collecting era started to emerge, we started to have more and more data. So collaborative systems, let's say, slowly took leadership on the algorithm rating system scale. So for the content-based recommenders, the main idea about this is it's dependent of the properties and it's independent of users' behaviors. So we can recommend something to a new user, even if we don't know anything, let's say, about well, not know anything about the current user, but immediately if that user interacts with the system, we can offer some kind of recommendation. So, for example, in this particular picture, if a user prefers, let's say, one type of beer, and we have a knowledge of the user that he purchased one type of beer, we can offer some other kind of item that is related to that specific category. So that basically, well, that relies on the fact that we already did categorization of all of our items. But what's cool about it is that there's no cold start problem. And we will see about the collaborative-based filtering that the problem is a bit of a, let's say, wider nature. The problem with these systems is that they are intuitive, they are fast, but they can't recommend anything generally new because the system will offer you the things that you already purchased, and that's about it. Concerning collaborative recommenders, they offer far better results than content-based, and they are not domain-free. So you don't need to have any sort of categorization between items. You can just have a, let's say, to make the thing simple, you can have users by IDs, items by their IDs, and to record an interaction between the user and the item, no matter let's say, the specific place of that item in some sort of categorization. To put things in perspective, for example, if we have two users, one of them, I don't know, likes to eat these two types of plates, the other user as well, and if one of the users likes some specific type of beer or soda, we can recommend that to the other user as well. So that's the cool thing, because we are recommending something genuinely new, and that is based on the behavior of a user that is, let's say, similar to us. If you think of it a bit, let's say, philosophically, collaborative recommenders are recommenders that are, if you are talking to your friend and she recommends something, that is basically a collaborative recommendation, because as, let's say, the time goes by, we have our friends that we share our interest in some particular way, and if we share our interest in, I don't know, in movies, we will let's say, take advice from our friend, should we watch a specific movie or not. And as we mentioned, hybrid recommenders, which are sort of a, let's say, combiner. We can use this with, I don't know, some weighting system, or we'll see it later. It's not that much important. And a few words, yeah, I initially excluded these slides, but as the conference went on, I realized that it's really okay to mention about, let's say, data science specific libraries that we are using and what's our, let's say, environment that we are working in. First and foremost, it's a SciPy stack. Let's say a stack that offers several libraries, and let's say for this concrete system, NumPy and Pandas are somewhat inevitable. Let's say NumPy as a main library that provides vectorization operations in multidimensional arrays. It sounds robust, but it is. And it boosts performance and speeds up the execution. Also, the Pandas is a really indispensable tool for data wrangling. So you will see the couple of examples later on. So just to know, to have it in the back of your mind what can be used as well. Scikit-learn as an inevitable part for machine learning done in Python. And it's de facto industry standard for machine learning with Python. And also Jupyter notebooks, which are really for also indispensable tool for exploratory analysis, because you can do the code, like modularly execute the code, the solutions stay in the RAM memory, you can run multiple visualizations and they will stay in place, and you will have a you can have a look. And it's also great because you can access your environment is your own web application. So if you have a URL, you can access it from anywhere, from work, from your home place, so it doesn't matter. Okay, for the dataset, I had a couple of ideas in mind, but eventually dropped out on them because I realized that if I use some really, let's say, cool, fancy dataset, I would spend too much time explaining the dataset, but the thing is that we should focus on recommender systems, not the dataset itself. But you will see, hopefully, that after this presentation, that you will, let's say, see the places where you can use recommender system algorithms for your own development as well. The dataset that I used is from the Movie Lens. It's a dataset that describes 5-star rating from and free text tagging activity from Movie Lens. It's a group lens part of the University of Minnesota. And basically, it's, as you can see, movies table. You have a movie ID, title, and genres. We'll see the genres. Let's say that's the categorization of the movies. Each movie can be part of several categories. And for the ratings table, it's obviously, okay, we have a user ID, movie ID, the rating, and the timestamp when the rating took place. Another thing which is important for recommender systems is that, for example, this representation of the dataset is, let's say, to reduce the space needed to save the data. And if you switch this to the real data set, we get a really large and sparse matrix, and which is inefficient to be stored like this. But it's, let's say, we need it in this form in order to execute our algorithms. So for let's say, this was like the complete data set, and this is like the simplified data set that I will use for explanation of the algorithms. So rows are representing users, columns are representing movies. And we already mentioned that matrix R is sparse, so 1% of populated values. And we will now switch to content-based. Let's say content-based recommender systems are, let's say, pretty much simple. If you want to do something on your own, they're pretty much straightforward, intuitive, and there's no reason that you couldn't try out doing something on your own already, if you haven't. So new user is registered into the system. The user makes a selection of categories of interest. For example, the genres of the movies. We should filter the movies from the desired categories, calculate the weighted ratings and vote counts. We'll mention why is this important, and offer best rated items from the chosen categories. It's pretty much straightforward. So for the weighted rating, it's the, let's say, simple term in explaining why the rating of 8 with 2 votes cannot be considered better than an item with rating 7.9 with 200 votes. So this is, for example, this specific equation is used for IMDb top 250 movies, and it works, let's say, pretty well. Not to enter into the details why is this, let's say, good, and for some other reasons, but this will give you a head start just to have a thought in your mind. This is the concrete Python code for this. Nothing spectacular. Again, it's using pandas library, and some things with wrangling the data are specific to that, let's say, particular library. So I wouldn't spend too much time on it. I will provide a GitHub repo which you can check out after the presentation. Yes, for content-based, some other thoughts. Later categories can be derived from user behavior. So it's pretty much important that if you say that you will be using, for example, you like one type of movies, but it turns out that you're watching some other type of movies, it's perfectly okay to offer movies from some other categories that you haven't entered in the start. Additionally, you can use metadata, make recommendations based on directors, actors, and so on. And for example, using also NLP, natural language processing on the movie synopsis, and let's say, chasing similar movies based on their description, using timestamp for the ratings following monthly, yearly trends, and so on. So you have a lot of things to be there. Collaborative filtering. Okay, we'll start with the, let's say, the main point of the talk. Collaborative filtering, we have two, let's say, well, ways of dealing with the collaborative filtering. First is neighborhood methods, and you will see that is also intuitive in some way. The thing is that for neighborhood methods, we have a matrix and the representation of it, and we can base user similarity and item similarity. So the thing is that we should find, we can search for similar users, or we can search for similar items, but using only the ratings provided in the matrix table. So the problem with this is how to compare two users. So in essence, this is just a vector, yes? And the thing is, plainly speaking, we are talking about similarity between two vectors. Not to go too much into details and to make this math bombastic, we have a couple of similarity measures that we can use, and depending on your particular scenario, you will, let's say, see, test what suits you the best. So these are just some of the similarity measures. There's really a ton of them. And for the, yeah, just to have the perspective of scale, for example, user space is much, much bigger than the item space. So for example, for Amazon, there's 310 million active users, and they are offering 12 million items currently. So, and the one also important thing is that users will have very few mutually rated items, and while items will have a larger number of users who have co-rated them. You will see why is this important. So for the user-based similarity, let's say this is the matrix that I already shown you. Not to go too much into details into code, but the thing is we've chosen a similarity measure. We'll take all of the users. For example, for a specific user, we'll compare that user to every other user, and it's just a vector comparison. And we'll choose the one that has the highest score. And afterwards, we'll check that user. This is just a representation to have those two vectors aligned next to each other. You will see that they really share quite a lot of things in common. And the idea is afterwards is to check the movies that our top similar user have rated, but our user that we are making a recommendation for hasn't watched it. That's one thing. And the other thing is that score is really, let's say, a good score. We won't offer a movie that has a rating, I don't know, 1 to the user. So that's, you can always, let's say, make this more profound and more complicated, but in essence, this is the basic idea. So we can use that for user-based similarity, and we can also use that for item-based similarity. You can see the point that it's really pretty much the same thing in terms of computation and the ways of getting the result. But there are really a couple of major points to consider. So two users, we already mentioned that generally have very few mutually rated items, while two items will have a larger number of users who have co-rated them. That means that the user-based, that means that the item-based matrix will be more stable. So when you enter a new rating into the system, you don't need to reevaluate or your, let's say, similarity, your computation all from the start. You will still have better recommendations. But also, item-based methods recommend obvious items because it's just a more advanced algorithm than the content-based, recommending only items that are in a way similar to them. In first content-based, it was similar because we put those items in the same category. And here they're similar because some users rated them similarly. That's about it. And now we are coming to the, let's say, interesting part. Second part is latent vector models. Model users in a reduced multidimensional space. That means like, I don't know what, but we will see the first thing that you should, if I want to explain one thing on this talk, it would be principal component analysis, because I think that all of you, no matter whether you have experience with it or not, you can understand it 100%. So, Principal component analysis is a mathematical procedure that transforms a number of possibly correlated variables into a smaller number of uncorrelated variables called principal components. You'll see in a minute what does it mean. The first principal component that counts for as much of the variability in the data as possible. When you check the math behind it, we won't go into math, and I won't explain this to you. If someone after this lecture wants to know more, I provided the slides and the links, so it's not a problem. But this is what I want to show you. If you have the original data set, and you have, let's say, data set on the left. If I told you that you can transfer that data set to the right data set, and that you would lose really, really small amount of the information, would that be beneficial to you? Yes, of course. For example, you can imagine that you have a data set that is, I don't know, has, I don't know, thousands of rows and thousands of columns. And if you, okay, you can't reduce that to the single, let's say, single row, but you won't use 1,000 rows, you can use 200 rows and to define, and you will have practically the same information that you have in the first. So it's a part of a lossy compression of the data, but you will see why is it good. So the main idea is that you can, data set on the left, you can switch to the data set on the right. If I ask you what's your, I don't know, reasoning behind how would you compress this data set in some manner, do you see some correlation between X and Y? Maybe. Some of you would realize that, okay, those are some points in the two-dimensional space. And we can, yeah, the main thing here, if you can check, is that with principal component, you will get the same amount of dimensionality of your data set. So X, Y, we have principal component 1 and principal component 2. Those points are the same. These data are the same. But in the first data set, variability of X and variability of Y, let's say not to use heavy mathematical terms, but variance, that's like dispersity of the data. If you check the X, it goes all the way from 2.2 to, I don't know, nearly 8, and for the Y, it's pretty much the same, yes. But on the second image, you see that for the PCA1 component, you have a really wide spread, and for PCA2, the spread is really, let's say, pretty much insignificant. So principal component analysis use this idea that we'll check the data, find the, let's say, dimension that offer the biggest variance, and we'll spread the data in that dimension. So, for example, for two-dimensional data, it's pretty much, in this example, it's easy to see the point. But the thing is that you will have data in some n-dimensional space also, but those coordinates, X, Y, and so on, also PC component 1, PC component 2, will go from biggest variance to the smallest variance, meaning that you can discard some amount of dimensionality on the end and still have the meaningful data. So that's the main thing that I wanted to communicate. For example, this is the 17-dimensional example of, I don't know, alcoholic and beverages consumption in, I think, UK, yeah. And if you check the data, if someone told us, okay, what's the, let's say, is it distinguishable between the countries, some pattern, we wouldn't have a clue, yes. But if we run the principal component analysis and we check only the first component, that first component will give the biggest variance between the data points, meaning that already on the first component, if you just plot the first component, we'll see that Northern Ireland has some really distinct, more specific patterns in their consumption of beverages and eating habits. Okay, not to repeat myself, this is about it. And this is really important just to, I will connect, let's say, this knowledge with the latent factor models as we introduced. Let's say, when the collaborative filtering really bloomed, when there was a Netflix competition held for improving their accuracy algorithm, and it was a 1 million prize, and winner beat Netflix accuracy by 10%, used over 500 different approaches. It was really, let's say, huge in the community. For latent factor models, what's the meaning? It's again some maybe a fancy term, but latent means hidden. And it provides better performance than neighborhood similarity-based methods. Why? The factors are called latent because they are in our data, but are not really discovered until we run the lower rank matrix factorization. We'll explain this in short immediately. The thing is, you have a matrix, we have a ratings matrix here on the left, and that's our original matrix that I already shown you a couple of times. The thing is that you can represent that matrix with two smaller matrices, which can have a multiplication of those two smaller matrices. What does it mean? The matrix on the left can be, for example, 1,000 by 1,000 and counting 1 million data points, yes. And for example, if you reduce the space, and we, for example, for the users and the movies, we see that the matrix is also for the users has 1,000 rows, but we'll have C number of columns, and we'll see what the number C is. And for the movies, the shape will be C times M. So it's also, let's say, 1,000, as we mentioned in this particular example. But that C is really important because we are what we are doing effectively here. We are running PCA component analysis on our matrix and getting users and running it on the movies and getting, let's say, some specific movies. PCA on ratings matrix will give you typical users are. When you imagine if we have 1,000 users, all of them are specific, yes? Yes, but when we look at them at their behavior, we can distinguish, for example, one typical users, or a number of typical users, and we can model their behavior with a lot smaller space than we have like everything. For example, I don't know what's that's used also, for example, sizing of the wardrobe. We don't measure each person specifically for every measurement of their t-shirt, pants, and so on. We have some classification, we use that. So it's also some way of compressing the, let's say, compressing the data. SVD will give you both of the PCA components in one shot. And we will now transfer to the movies where you can really see what is all about. So for example, if we have the matrix on the right, simplified dataset, those components are, let's say if we could say for each of those components, for example, if we have for example, if we have movies, we can define that there's something called, for example, like an action movie, yes? Or a comedy movie or a romance movie. And we can define that as a specific component. And for each of the movies, we can say this movie is like 10% comedy, 20% comedy, or 60% comedy, and that's about it. And when we get and for the users as well. And the thing is, with this SVD, is a cool thing because those principal components that exist in the user space exist in the item space as well, and they are the same. So we are reducing the, okay, this is only the calculating part. I didn't want to offend you offering matrix multiplication or dot product here on the slides. But for a specific rating in the matrix R, the thing is that we pre-computed these two matrices that are pretty much can be efficiently stored. And for each of the ratings, we just calculate the dot product between the row P and the column Q, and we'll get our result. The problem here is because our matrix is sparse and it's not, the SVD is not defined. So not to go again into details, if R was dense, we could compute both matrices easily, but we can't. And the first option was to use some sort of heuristic to fill in the missing values, some mean values or stuff like that, but that's really not okay to fill up 99% of your data with some data that doesn't exist. And we can have some approximation, let's say, solution using stochastic gradient descent. We won't go into details about that as well, but you can check it out afterwards if you are interested. And the main thing is we can use a library already. So we have our matrix. We can run the SVD, surprise library. I advise you to check it out. It's really cool about various implementations of the recommender systems. Then again, if you have some algorithms of your own, you can check the the quality of your algorithm, because not to go into, let's say, strictly data science related projects that you have training sets, test sets, and stuff like that. So it's pretty much made automatic using this library. So the thing is, we'll have our matrix. We'll run SVD from the library, and we'll check, for example, for the user 19. We'll check SVD predict, for example, for user 19 and movie ID 2. We got a prediction of 3.12. And the realistic prediction is 3.0. So it's, let's say, a nice example of forecasting the prediction of the user. Okay, some closing remarks. I want to emphasize that the recommender systems are not reserved only for the product item recommendation. They can be used in really myriad of situations. It's a great tool to model any kind of interaction between some items, services, and so on. There was a really nice paper that I checked for this presentation, but I realized that it's going to be like too much to explain the whole paper and the data behind it. Presentation material, both presentation and corresponding Jupyter notebook can be well checked at this address. Sorry, I'll share the slides as well. And this list of, I will update this list also, so you can, if you are more interested in finding out various things about recommender systems, I advise you to check this out. So that would be it. If you have.
Thank you, Mladen. We didn't receive any questions on the Slido, so if anyone is interested.
Yes.
Go,
please.
Ranka, just a second. Wait. Hold on. So the outside guys can hear you.
First of all, thank you very much for a very, very interesting presentation. Full of several information that can be relevant for a lot of people here. But my question is related to phase of preparation before you do reduction of space. Have you maybe analyzed, for example, when you have one feature, do you first see which distribution is in this particular feature? Is it maybe Gaussian, normal, or uniform distribution? And if different distributions go differently into next phase. For example, if it is uniform, I suppose that it doesn't help much in the next phase, but if it is some kind of normal distribution, it will be relevant for classification later. Thank you.
Yes, thank you for the question. I mentioned the one of the first slides that it's let me check for the that for a lot of yes, for a lot of ratings and users, the Pareto principle is taking place. That meaning that if we have like items on the X scale and the popularity, the number of ratings that it received from the users, it will all of the ratings will follow this pattern. And what's really, let's say, interesting is that these long tail niche products that exist are something that will make your recommendation really good. Because these, let's say, cool products that exist, there's really a lot of us that will appreciate them. I don't know, some specific type of, I don't know, PC, computer, laptop, or something else. But when you go into to define particularities of each of the items or the users, then we will not have that much of statistical support in claiming something. So it's, let's say, a harder problem for. Well, that's like with all things. If you are deviated from the, let's say, mean behavior, it's much harder to interpret your behavior or forecast what will you like or dislike. So, because there is not much data, not much data there.
Thank you. Any more questions from the audience here?
Thank you.
No? Okay, one more big applause for Mladen, and we'll close this session.
My name is Mladen. I just finished my talk about recommender systems, collaborative filtering, and dimensionality reduction. And I don't know, I have to say that I had a really, because my talk is like on final day, there's only 2 talks left, but I really enjoyed the whole conference and I'm really looking forward to the next one.